Okay, okay. Okay, so let's start. So today we will cover a summary from week 9. So these are the topics I want to cover. So first we'll start with maximum and minimum value of a function. So suppose a function is given to us, then how can we find out maximum and minimum value of that function? I'll explicitly define what is the meaning of max and minimum value for any function. And we actually have a rule to compute these values. It's known to be the second derivative test. So we use this second derivative test to find out max and minimum value of a function. So after that, we will go to Riemann sum. So what is the concept behind Riemann sum and how we can compute the area under the curves. So that means an area bounded by a curve and bounded by some line segments. So we will talk about this topic too. And after that, we'll go to antiderivative. So what is antiderivative means? So it's just the inverse process of differentiation. Okay, so we'll also talk about this. And then we have a very nice theorem. It's known to be fundamental theorem of calculus. It's a very basic theorem which actually relates these two topics, that is Riemann integration and the antiderivative topic. So these two things we can relate using this fundamental theorem of calculus. Okay, so this is the overview of today's lecture. So I have shared you one PDF over the chat. That PDF contains all the required formula of differentiation and integration, so that I won't write it down explicitly the formulas, because you have to remember each and every formulas, and you will remember once you start practicing more and more problems, right? So just download it and write it down if you want. Or else, if you want other formulas, you can find it over the NCRT or in our course lectures too. Okay. So am I audible clearly now?
Yes, ma'am, you're audible.
Yeah. So let's start. So first of all, we'll start with maximum and minimum value of function. Okay. But before this, try to understand two types of points. Okay. One is known to be the turning point, and another one is the critical point. Okay, so what are turning points and what are critical points? So first of all, we have a function. For that particular function, we define a point is known to be a critical point or a turning point. So uh, we have a point x naught comma y naught is called to be a turning point. Turning point if a function f changes its nature at that point. So changes its nature means it is first increasing and then decreasing, or first decreasing then increasing. So that means it will change its behavior from increasing to decreasing or decreasing to increasing. So such type of points are known to be turning point. Okay. So turning point means a point P is known to be a turning point if at this particular point function changes its nature from either increasing to decreasing or decreasing to increasing. Okay. So now what is a critical point? So in critical point we have to consider two types of point. First point is, so a point Q is called a critical point if first thing is f is not differentiable at Q, or if it is differentiable if f is differentiable at q, then the value f of x1, suppose q has coordinates x1 comma y1, then the value of derivative at that particular point should be equal to 0. Okay, so that point is known to be a critical point. So in critical point, we will consider two types of nature. First thing is either function should not be differentiable at that point. So that means f is not differentiable at q. And the second thing is, or if the function is differentiable, its derivative should be equal to 0. Then that point is known to be a critical point. Okay, so now what is the relation between turning?
So
Yeah.
what you're saying, ma'am, is in the critical point, the curve, the function should be discontinued.
Yeah, either it should not be differentiable or it should not, or if
Yeah,
it is differentiable, then derivative should equals to 0.
yeah. If it is not differentiable, means a discontinued function, right? It's
No,
not
no,
continuous.
it is possible to have continuity.
Okay,
Right, right.
right. Continued, but it cannot be differentiable.
Differentiable.
Whereas if it is differentiable, then the slope should
Derivative
be
should
zero.
be equal to 0.
Yeah,
Yeah,
that means slope should be zero. There is no
right,
change
right.
in no change in y value when there is a change in x value.
Yeah.
Okay,
But it's better to relate it with derivative.
derivative. Okay,
Derivative means
fine.
the slope of tangent.
Slope.
So that
Yeah,
means if derivative is 0 means tangent is nothing but parallel to x-axis,
parallel to
right?
x-axis. Yeah,
Hmm.
that's what
So
So
now,
change
like
in.
yeah,
if I give you an example like y is equals to 2, so dy by dx over here will be 0, right?
yeah,
That's a non-differentiable function.
y is equals to 2 is a straight line. It is differentiable everywhere.
It is differentiable everywhere.
Yeah. So if you are saying y is equals to 2, then it's nothing but a straight line, right?
Yeah.
So it is differentiable everywhere. Its derivative is equals to 0 everywhere.
Zero. Slope is zero.
Yeah. The
So
slope is
can
0, right?
you give an example where derivative we cannot find a derivative?
Yeah, this modulus function, right? Modulus of x. It is continuous, but we cannot find derivative because there is a sharp edge at point 0. Right? So here you can draw several tangents. If you want to interpret in graphical ways, you can draw several tangents. That's why this point is not differentiable. Or else just by definition, left hand derivative not equal to right hand derivative. So you can use that too. Okay, now how can we relate turning point and critical point? Is there any doubt? Just let me know. Okay. So now, as we learn that what is a turning point means, at turning point, function is changing its behavior from increasing to decreasing or decreasing to increasing. And in critical point, we have two cases. First case is function should not be differentiable, or if it is differentiable, then the derivative should equal to 0. That point is known to be a critical point. Okay. So now, how can we relate these 2 points? So suppose if we have a function, uh, and it has a turning point at a point P. So suppose this is a point P and this point is a turning point for a function. Then what happens? Function is changing its behavior at point P. So the function is first it is increasing, right? So in the graph, suppose this is a graph of function f, then you can observe that before the point P, function is having an increasing behavior, and after the point P, it is having a decreasing behavior. So that means at a point P, function is changing its nature, right? So that means we can say that P is a turning point, right? But we can easily observe that at point P, the function is also differentiable. And if we draw a tangent at point P, this tangent is nothing but parallel to the x-axis, right? So we can say that at point P, the derivative of f is nothing but 0. Okay, so if you assume x0 comma y0 is the coordinates of point P, f dash at x0 is nothing but equal to 0.
So turning point can be a critical point if you
Correct,
consider
correct,
the second point of this right side condition.
right. So that means turning points are critical points, are also critical points.
Okay, always or
Yes, always.
always. Okay. But a
Okay,
critical point need not be
point.
a turning point because your first condition is not applicable in that case.
Correct, correct. Yes.
Okay.
And also, if it is differentiable, then only we have an example where it's not a turning point. You can consider the graph of y is equals to x cube. So this graph will look like some like this. Okay, so here at point 0, you can observe that before the point 0 also function has increasing nature, and after the point 0 also function has increasing nature. So that means at 0 comma 0, function f of x is equals to x cube is not changing its behavior, right? Is not changing its behavior, right?
Right.
But we know that f dash at 0 is simply 3 into 0 square, which is 0 ultimately, right? So that means a critical point need not to be a turning point. Correct? So this is a relation between these 2 points. So that means a turning point is always a critical point, but a critical point need not to be a turning point. Is that clear?
Ma'am, quick question. If you go back to the earlier course, earlier lessons, we said that graph at x0, x square, which is parabola, has a minima or maxima, which is vertex is minus b by 2a.
Correct.
So there we are not doing any differentiation of a function. We are just come up with the
By
formula.
observing the graph only we can say, right?
Okay.
Just by observing the graph also you can judge which value is the minimum value of a function.
There the differentiation is applicable still, even the
Yeah,
parabola
there is
x
also
square.
this test is applicable.
Same. If a function is given as x square as a degree, we can differentiate and come to the same point as maxima or minima. The way we are using the minus b by 2a as a vertex formula. Is that correct? My understanding?
Yes, that's correct. Because we reach at minus b by 2a using differentiation only.
Okay, understood. Okay, ma'am. Please continue.
Okay. So maximum and minimum value of a function. So what are the maximum and minimum values? So suppose you have a function like something like this. Then in this function, there are several points around which if you observe the value of function, that at that point, the value of function is either maximum or minimum. For example, if you consider this point, suppose x is equals to minus 2. So at this point, the value of function is minimum. So that means if you take a very small neighborhood or very small very small interval near x is equals to minus 2, then all the functional value, whatever functional value we are attaining over the small interval, the value f of minus 2 is the minimum. Right? So such points are known to be local minimum points, right? Or local minima. So we say at x is equals to minus 2, f has a local minimum. And here I am writing a local minima means it is possible for a function to get more than one local minimas or more than one local maximas. And similarly, what is a local maxima means? So a point, suppose here x is equals to minus 1. So if you take a very small neighborhood of around x is equals to minus 1 and consider the functional values on this particular interval, then you can observe the value f of minus 1 is the max value. So such type of points are known to be local maxima. Again, a local maxima, so it is possible for a function to gain more than one local maximas. Okay, so now what is a global maxima or global minima means? Among all those local maxima, local minima, you will find again a maxima. So for example, here this point. So suppose here x is equals to 3 we have. So you can observe that this is the point where function having a global maxima. Because if you compare all other points, all other values of function, those values of function are less than or equal to that particular value. So this type of
Hello, ma'am, you're there? Others? Hello. Any other people are okay? You're there. Okay, so we lost her. Okay. Hello.
Oh, hello, am I audible?
Ma'am, no, ma'am. There was a break in between. Can you please?
Hello?
Hello. Are you able to hear me?
Yeah.
Ma'am, there's a break in between. Can you please repeat again?
Okay, yeah, sure.
There was a short
Yeah,
break in between.
of the screen. Got lost. Hello, am I audible now?
Yes, ma'am. You're audible now.
So I was talking about local maxima and local minima. So local minima means, So for example, here we have a point x is equals to -2. So you can observe that you can take a small interval around x is equals to -2, and if you consider the functional value is at in this particular small interval, you observe that the value f of -2 is the minimum value, right, over the small interval only. So such type of points are known to be local minima. Okay, and similarly, if you consider the point x is equals to -1, then you can consider a small neighborhood around the point x is equals to -1. And if you observe the functional value, then the value f of -1 is the maximum value, right? So this point is known to be a local maximum.
So, ma'am, if you take f of -2 as a point of or critical point, if a
Hmm.
small increment is taken either to the right or to the left, there will be a change in the value. Is that what you're
Yeah,
saying? Or
right,
it will go from minus to plus on the other side.
right. So this,
Having, okay,
hmm,
okay. And same with
f of
the
-1
f
too.
of -1 also. Okay,
Yeah. So
okay.
actually what happens, so here you will get some negative derivatives, here you will get some positive derivative. So
Hmm.
at this point, the derivative will become 0. So here also you can observe that if I draw a tangent at the point -2, that tangent is nothing but parallel to x-axis. So
Okay,
we can say that uh, if f dash at x naught becoming 0, then it is possible to have a maximum or minimum value at that point. Okay, so I'll also state this one. But first understand local maxima, local minima, global maxima, global minima. So among
okay.
all the local maximum values, if you take the highest one or the largest one, that will be your global maximum. Okay, for example, here in this graph, if you consider this point x is equals to 3, then the value of function at this point is bigger than every other value of a function, right? So such type of maximum are known to be global maximum.
So
So
what
now,
happens if you have more than two global maximas of equal value? So it will
it's
be
not
one.
possible, right?
Okay. Oh,
If we have two global maxima, then one of them should be less than or equal to another. Otherwise,
yeah,
they will be equal.
yeah. They should be
Hmm.
equal. So we
Yeah,
can take either of the point because when they are equal, they are two global maximas, but at two different locations of the
yeah,
graph,
it is
the
possible
domain.
to.
Then how do
Yeah,
we how do we take? For example, x equal to 3 is there, x equal to 5 is there. Let us say, for example.
yeah.
Or let us say x is equal to -3, x is equal to +3, where we
Hmm.
have both the same y values, which is a global
Hmm.
maxima. So which
Hmm.
one should consider as a global maxima in that
Yeah, you
case?
can consider anything because
Okay.
whenever we ask about global maxima, we ask the value of function, not the input point.
Okay. No, always value of y.
Yeah, always because in global maxima we want the value of y, right?
Oh, okay.
Otherwise, we will ask about local maxima, local minima.
Right. Okay. Then
Okay,
similarly, global minima is the least of the
minimum
values,
values. Yeah.
minimum values. Okay.
Okay.
Thank you,
So
ma'am.
now the question comes, how can we find these points, right? So for that we have a test known to be second derivative test. Okay, so we will apply a second derivative test. So as the name suggests, second derivative means we have to compute the f double dash of any function. Okay, so this test works in two steps. So the step number one is find all those points where f dash at x is equals to 0. So ultimately what we have to do, we have to solve this equation f dash of x is equals to 0 and find out all those points where derivative becoming 0 ultimately, right? Because why do we need to find this one is, so one thing is if a function, if f has a local maxima or minima at point x naught comma y naught, then the derivative at that point f dash of x naught will always be equal to 0. Okay, so that means if it is possible to get a maximum value at certain point, then we can surely say that the value of derivative will become 0. An obvious reason is you can observe in this graph too, where so at any point where we are having maximum or minimum value, if you draw a tangent, that tangent is nothing but parallel to x-axis. So it is so that means if you want to find out minimum or maximum local maximum minima, you have to first consider those points where the function's derivative is vanishing. That means f dash of x is equals to 0. Now the second step is Step number 2 is we need to find out the value of double derivative of a function. So it works in 3 cases. First thing is, suppose f dash at x naught is equals to is strictly greater than 0, then we can say that at x is equals to x naught, we have a local minima. Okay, if greater than 0, then local minima. Second thing is, if the second derivative at that point is less than 0, then we will say at this point x is equals to x naught, we have a local maximum. Okay, so greater than 0, then we have a local minima. Less than 0, we have a local maxima. And the third thing is, if second derivative at that point is equals to 0, then in this case, we will say that this test actually fails here. So we cannot conclude anything from the second derivative test. Okay. So I'll repeat how we need to find out local maxima minima. First thing is filter out those points where the first derivative becoming 0, and then at those points find the values of second derivative. So if it is positive, then we have a local minima. If the value of second derivative is negative, then we have a local maxima. And if the value of second derivative is equals to 0, the test actually fails here. Okay, is that clear? Yeah, it's a very easy test to apply.
So,
Yes, ma'am.
ma'am,
Yeah.
if you go back to the graph which you just drawn in the top, yeah, just hold on for a minute. So if you see carefully, you have 1, 2, 3, 4, 5, 6 change in directions, right?
Yeah.
So assuming there's an equation which defines this graph, let us take hypothetically for time being that you are given an equation which defines this curve, this function, which
Yeah.
has six points. Now
Yeah.
what you are saying is first you take at each point, first you do the first derivative of that function.
Yeah. Mm-hmm.
Whatever x square, x cube, whatever you give, you would make a first derivative, and then you introduce each of these points, whatever your turning points, that value of x value you induce into that derivative function, and
Correct.
see which of the 6 points, which of the 6 numbers you introduce, you are getting y equal to 0 or f
Right.
dash equal to 0. Now, whichever you are getting f dash to 0, you eliminate all those points. Or just leave it there. Then you do a second derivative of the same function, and then you introduce again those 6x not x, because again you need to introduce the same 6 points into the second derivative.
Yeah, same 6 points.
Same
Whatever
6
filtered point we have here from this equation, you just have to substitute it into second derivative.
But then what is the point of having the inducing the 6 values into the first derivative when you are not even eliminating anything from that?
Yeah, we are eliminating all other real numbers now. So if you solve this equation,
Okay.
you are getting some 6 values only, right?
Correct. But
So
6.
if a function from R to R, then you are eliminating so many numbers, right?
Okay.
That's the reason.
But invariably, okay, if here the graph is given, so we are able to tell what is the turning point and induce. But in actual scenario, you may not be given a graph. You may be given only a function. In that case, you don't know which are the points. Okay, understood. Okay.
You just have to solve an equation. So either it will be a cubic or quadratic, something like that only. You
But in the
won't get the.
question, but they will give the points, ma'am, turning points in such a problem. They will say,
No, they will
can you
give you a
find?
function. They will give you a function. For example, if I give you a 4-degree function, so suppose f of x is some x to the power 4 by 4, right, plus x
Right,
cube, something like
right.
this.
Whatever.
Then you can differentiate. It will
Correct.
be a cubic, and then it will be easier. Either it will use heat and try method.
Okay.
Mostly it will use. They will ask about heat and try method.
Fine.
Right?
Okay, ma'am. Please continue. Sorry, I got digressed.
Yeah. No, it's okay. If you understand a concept once, then it will be okay for every time,
Yeah,
right?
sure.
So that's all about maxima minima. So it's a very easy concept. There is only one test you have to apply, and which is this particular test, right? Second derivative test. Now let's go to the next topic, which is the Riemann sum.
Here we don't we have to find the global maximum.
Global maxima is nothing, but you have to choose the maximum value from all local maxima, right? So it's a easy one. So if you have all local maximas, you can just pick the largest value,
Okay.
right? Let's go to now Riemann sum. So what does Riemann sum mean? So first of all, what is the problem we want to solve here? So we want to find out area under the curve or area of any particular region. So initially we know how to find out the area of a square, right? So area of a square is nothing but the square of any of the each length, right? So if the length of side is a, then area is nothing but a square.
A square.
Right. If we have a rectangle, how can we find out the area? So the idea is to decompose this rectangle into several squares and then use that area of square to find out the area of rectangle. Similarly, if you have a triangle, then how can you find out the area of a triangle? So the idea is again make a rectangle over here or decompose this area into some known area. Okay. So the idea is decomposing an area into some known figure area. For example, the if you want to find out the area of rectangle, decompose area of rectangle into some squares, right? You will get area of rectangle. So we use this particular idea only to find out area under any curve. So let me take a figure here. So suppose we want to find out area under this particular curve. Suppose this is a function's curve f. So here I am using the word curve, right? So curve is nothing but a graph of a function. Graph of a function in plane. So in a plane, if you draw any graph of a function, that graph is known to be a curve. So don't bother about the word curve means. So suppose I have a curve here or a graph of function f here, and I want to find out what is the enclosed area here. So that means I want to find out what is the value of this particular area. Okay, so our idea is decompose this area into some known areas. So we know how to find out the area of a rectangle. So what I'll do, I'll try to decompose this area into several rectangles. Okay, so but in a rectangle, there are two things for a rectangle. So one is the height of a rectangle, and another one is this particular width of a rectangle. Right. So we want to know what is the value of b, and we want to know what is the value of h. Okay. So here, if I want to insert some rectangles, I have to fix two values. I want to fix this b. I want to choose what is the height of each rectangle will be, right? So for width, what I'll do? So suppose here we are starting with 0, but you can start with any number. So for time being, assume that this is somewhere. This is your origin 0, comma 0, and here we have a point a. Suppose this is x is equals to a, and this is x is equals to b. So what I'll do, I'll introduce some points in between x and x is equals to a and x is equals to b. Okay. So I'll introduce some point. Let's name it to be x1, x2, x3, x4, x5. And for time being, suppose I have introduced 6 points. And I'm saying that I have this set of point x0, which is equal to a, x1, x2 up to x6, which is equal to b. Okay. And the reason why I'm doing this, because I can take control of b. So what I'm saying is, so we can take the breadth of each rectangle to be the length, to be the distance between each point. So that means the breadth of first rectangle will be x minus a. Sorry, x1 minus a. The breadth of second rectangle will be x2 minus x1. Right. So whatever value we have here over the x-axis, these values can be considered as the breadth of our rectangles. Okay. So now we have fixed what is the value of b. So now let's talk about what can we take as a height of each rectangle. Okay. So as a height, we can take several things. So one thing is you can consider the very left endpoint of each this intervals, right? So for example, if we have a comma x1, so I can say that okay, you will take f of a as the height of rectangle, right? Height of rectangle. So it is possible to take the very left end point of each interval as the height of rectangle. Okay, so suppose now I'll take x1. So this will be our height. So now this will be our height of rectangle. If you consider the left end point of each subinterval, then that will be your height of rectangle. Right. So here you can observe that okay, area of the region somewhere approximate the area of each rectangle's sum. Right. If you sum all the rectangles areas, then the area of region is somewhere approximate to the sum of areas of these rectangles, right? So that means here we are getting that okay, area is somewhere approximate to the summation of each rectangle's area. Okay, so what will be the rectangle's area now? rectangle's area will be f of a, because the first point is f of a, right? F of a. So this is our height h into the breadth. Breadth is what? x1 minus a plus f of x1 into x2 minus a, x2 minus x1 plus f of x2 into, you can compute the area of each rectangle and then sum it. Okay. So now here we are getting some kind of approximation. Okay. But what happen if we change the breadth, right? If we change the value of b, then what will be the corrections, or what will, is it possible to get a better approximation, or it is possible to get a better thing here to approximate the area under the curve? So the answer is yes. So if you consider a rectangle which is nearly half of the breadth of the first ones, then you can observe that these rectangles will uh, much more efficiently cover the area under the curve, right? So here, if you just shrink your breadth over the half, or whatever it is, so then it is possible to get a better approximation or a better thing, right? So that means if we shrink the breadth of each rectangle, so if we shrink it, we will get better answers.
So more the thinner slice you slash, the better
Correct.
the accuracy of the area. Is that what
Area
you're
will become, right?
okay?
So the answer, so the fact is correct. So if we shrink our breadth of each rectangle, we'll get a better and better answer for area under the curve, right? So but how can we, up to which point we can shrink it? So the answer is we can make very 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 thinner slides. So for example, very thinner, so a slice of breadth, suppose 0.000, so many zeros are there and one, we can do that too. But for this, how can we approach mathematically? Okay. So here what we want to do, we want to take this b to 0, right? What we want the breadth of each rectangle to be very, very closer to 0. So for that, what we can use limit to do this, right? So for this particular condition, we can introduce a limit. Okay. So we have a problem, and for that solution, we have to somehow introduce a limit b going to 0, right? Where what is b? B is the breadth of each rectangle. Okay. But here, what we are doing, we are also introducing a points, right? So that means as b goes to 0, the number of points here should increase, right? Because if you want to take a smaller breadth, here you need to consider much more points, right? Here, as initially I have considered 6 points, but in place of 6 points, if I have considered 10 point, then there are 10 number of rectangles, right, in the same region. So the automatically the breadth will become smaller. So for that, what we do, we will first introduce a particular term for these points. Whatever points we have taken here, this x1, x2, x5, x6, we will introduce a name to be partition, right? So we will say that we have a partition of a closed interval AB, which will take care of choices of this particular points, x1, x2, x3, and so on. And that will also take care of this particular limiting condition, that limit b going to 0. Okay. So what does a partition mean? So let me introduce you. So partition of closed interval a comma b. So it is nothing but again a set p, which contains now the points in between a and b. So it is nothing a set of all points between a and b. And again, it's a finite set. Okay. So it is a finite set of points between a and b. So yeah, we don't need to consider it finite, because there are cases where the partition can become infinitely many points. So ultimately, a partition is nothing but a set of points between A and B, right? So you can take some A is equals to x0, x1, x2, x3, up to some n number of points is equals to B. Okay, so this set is known to be a partition of closed interval a comma b. So what we are doing, we are just giving a name to choosing points between a and b. So we say if you want to choose a point between a and b, just take a partition p of closed interval a comma b. So now, with respect to this partition P, we will define another term which is known to be the norm of P. Okay, so norm of P is denoted by this symbol, the two lines around P. So what is this norm of P? So norm of P is the maximum possible length of a subinterval. Okay, so let me introduce what is a subinterval first. So here, as you introduce the partition, so this partition, so actually this the name partitioned means actually this particular subset partitioned the closed interval a comma b into several several subintervals. So what are those subintervals? So those subintervals are a comma x1, then x1 comma x2, then x2 comma x3, right, and so on. At the end we have xn minus 1 comma xn. So this partition actually partitioned the closed interval into several subintervals. Now related to each subinterval we can define the length of each subinterval, right? So we can define what is the length of each subinterval, right? So the length is nothing but x1 minus a. So that means the end point minus the previous point. So the length of this subinterval will be x2 minus x1. The length of this subinterval will be x3 minus x2. The length of last subinterval will be xn minus 1. Or you can say that simply b minus xn minus 1. Right. So what we have done initially, we have a partition of closed interval AB. What is a partition of closed interval AB means? We have to select some points between A and B. So now this partition will actually partition the closed interval AB into several subintervals. So for example, a comma x1, x1 comma x2, x2 comma x3, and so on. Now, related to each subinterval, we can define the length of each subinterval. What is the length of each subinterval means? The end point minus the first point's value. That means x1 minus a, x2 minus a, x3 minus a, and so on. So now what will happen? We will choose the largest length here. So choose the largest length, and that largest length is known to be the norm of P. Okay, so if you have a partition, that partition will partition closed interval AB into several subintervals. For each subinterval we can compute the length of each subinterval, right? And that length is known to be and among that length, if you choose the maximum length, that is known to be norm of P. Okay, so here just understand what is the norm of P. So whenever we want to find out integral using this particular Riemann sum, we actually take the regular partition. Regular partition means we will take the length of each subinterval as 1 by n. Okay, so whenever we use a partition, so usually the norm of P is nothing but 1 by n. Okay, so this is always a fixed number, or at max time it is nothing but a 1 by n. So we try to partition a closed interval AB into some n number of subintervals. Now this n could vary. It is possible that you want to partition it into 2 subintervals or 3 subintervals or 4 subintervals, right? So according to that you can select your points x0, x1, x2, x3, and so on. So this number is known to be norm of P. So here in a figure, if you observe, so suppose let me draw another figure. So here suppose I have taken this particular partition. Okay, so suppose this is your 0 to 1, right? So here I have taken 1 by 5, 2 by 5, 3 by 5, 4 by 5, and 1. So here we have a closed interval 0 comma 1. For this closed interval 0 comma 1, I have taken a partition P with containing the point 0 comma 1 by 5, 2 by 5, 3 by 5, 4 by 5, and 1. Okay, so now here what will be the norm of P? So norm of P means you have to choose the largest length between each subinterval. But here you can observe that the distance between these 2 points is nothing but 1 by 5. Here also distance is only 1 by 5. So here is also distance is 1 by 5. Distance is 1 by 5, and so on. So here norm of P is nothing but 1 by 5.
Ma'am, one question here. In
Yeah.
this picture, what you have drawn, the partition is the complete curve, the area under the complete curve. Is my understanding right? That is between
No.
0 and 1.
No. So partition means just choosing some points between 0 and 1. We haven't gone to area. So because we want to apply this limit thing, whatever this is here. I want to tackle this thing, the limit
Correct.
b going to 0, right? So for that, how we can choose the points between a and b? So for that, we can introduce a term known to be partition, which will say that okay, you can choose points between a and b like this. And what is the norm of p? Norm of p will be the whatever largest distance you have chosen, that will be your norm of p.
One thing I'm not able to understand in this explanation is
Mhm.
in this curve, you're drawn 5 rectangles,
Yeah.
right? So each rectangle is a partition. Is that
No, no,
what
no.
you're saying?
No, no, no. See, partition is just a set, just a subset between 0 to 1.
Okay.
So here, if I remove this rectangle, so a partition is these points. This 1 by 5, 2 by 5, 3 by 5, 4 by 5, and 1. This
But
is the partition.
the partition points are covering the complete domain that is between 0 and 1, right? That is
Yeah,
what.
yeah. So not covering the domain, we are just choosing some points between A and B. That's all.
Basically our area of interest is between 0 and 1, and you are
Yeah,
partitioning that between 0 and 1 into multiple subsections,
correct, correct. So because
right?
that only,
And so
hmm.
my question is, each subsection is a partition, or the overall 0 to 1 is a partition, is what my question, doubt.
So overall 0 to 1, whatever point you are choosing, that is
Huh,
the partition.
okay. But if
Okay.
I can always choose some in between point also. For
Yeah, you
example,
can always
I'll
choose.
say
It's up to you.
my partition is between 0 and 1, but my
Hmm.
area of interest is between 2.5 to 3.5. Can I make that statement or no?
No. So if you are
No.
saying your partition is of close interval 0, comma 1, then you
Huh,
need to take points 0 should obviously should be there and
right.
1 should be there.
Okay. So the
In
partition is
between you
always
can say
between
like
0 and
this.
1, and
Yeah.
my sub partitions are whatever I am saying, 1 by 5, 2 by 5, 3 by 4, 5 are sub partitions.
Yeah, correct.
And the length of the subpartitions can vary, is what you are saying.
Yeah.
That is between the
Yes, yes.
0 and 1.5. Here in this scenario, you are having a fixed 1 by 5 as a partition distance.
Length.
But in
Hmm.
actual scenario, in the real scenario, I can even modify that is between 0 and first point can be something. First point to second point can vary.
Right,
Second to
right,
third
right.
point can vary. Is that what you are
Yeah.
saying?
Huh.
Okay,
That
right.
is
Understood.
possible to take.
Okay, okay.
Now here, what happens if I introduce more and more points in the partition, then we are automatically getting more and more rectangles, right? So initially I have introduced only 5 points, right? 1 by 5, 2 by 5, 3 by 4, 4 by 5, and 1. But if I introduce 10 points, so that means if I introduce more 5 points, here you can observe that you will get much more rectangles, right? So the number of rectangles increases as we are increasing the number of points in our partition. Correct. So
Yeah.
here what is other thing is happening is this norm p is also getting lesser, right? So here this is becoming less if we
Hmm.
introduce more points,
The denominator of the n is increasing in that
right?
case.
So here n is increasing, so norm is getting 0. So that means here we can observe that if we just apply limit norm p going to 0, then we can take we can take so many rectangles with nearly zero breadth, right? Am I right here? If you take norm p going to 0, this particular limit, if you apply, then you have to make this particular distance, that means distance between 2 points of your partition, you have to make it smaller and smaller. So that means you will get more number of rectangles in between. Is that okay?
Yeah, I understood, ma'am. But I don't know others. I'm not sure. Okay.
Yeah, it's okay. If you don't, this is just a theoretical part.
Yeah,
I
yeah,
don't want you to just, integration is something come from the heaven.
yeah, yeah.
Not that like. Okay. So
No,
here, if you take limit norm p going to 0, then you can consider more and more rectangles in between this particular figure, right?
yeah.
So
My
this is yeah,
my understanding is the thinner the slice is, when the curve is actually it's not a sharp curve. It's sort of a bending, right? The slope.
yeah,
So if you have a bigger rectangles, then there is always an error because the rectangle
mm,
is going outside the curve.
correct,
So
correct.
there's an additional error is there. So if you
Mm,
slice it very thin, so your rectangle is always within the curve. Only thing is the rectangle height has to be reduced.
yeah,
As you are moving from 0 to 1, you are coming from 0 to 1, the curve is sloping down.
Yeah.
So you have a thinner rectangle. So height of the rectangles will keep reducing as you come towards the 1. Thereby you are reducing the error because you are having a very thin slices. That is my understanding.
Hmm. So yeah, that's correct. So ultimate goal is to introduce more and more slices in between that particular region. Okay. So let me write down what is a Riemann sum is. So we say a Riemann sum is the sum. The Riemann sum is actually defined for each and every partition. Okay. So suppose if you have a partition P, then the Riemann sum is nothing but, let's forget about the Riemann sum. I'll simply define what is the integration means. So an integration a to b f of x dx is actually this limit. So limit norm p going to 0, and here we have to sum the area of each rectangle. Okay, so suppose I have here n number of rectangles, right? So I can say that I is ranging from 1 to n, and f of xi into del xi. What is this del xi? Del xi is the length of each subinterval. So that means xi plus 1 minus xi. So this is the Riemann sum formula. So here you'll observe that this particular factor is actually what? So this factor is the area, sum of areas, right? Same sum of area of each rectangle.
But this formula will work only when the intervals are same, no, ma'am? But you said you can always vary the intervals.
Yeah, but see, if we are able to take same intervals, then we won't vary it too much, right?
Oh, okay. So, but
Although
my question is, this formula is applicable only when the delta xi is same across all the subintervals.
no, you can also define delta xi is related to each subinterval, right? Xi
Okay.
plus 1 minus xi. So it's up to you.
Then you have a different terms, multiple
Yeah,
terms with varied variable. Then the delta xi can become xi, x1, x2, x3. So not
yeah.
only xi, oh, okay, you have both xi and delta xi is two separate. Okay, understood now. Thank you.
Okay, so here
Understood.
norm p going to 0, we are taking care of that we are introducing more and more rectangles in between our area. So this is how integral is actually defined. That integration is a limit of certain sum, and this particular sum is known to be the Riemann sum. Okay, this is your Riemann sum. So if you are not able to understand Riemann sum, that's okay. But you need to understand how the integral actually become. What is the meaning of integration e to b f of x dx? So it's a limit of certain sum, and that particular sum is known to be a Riemann sum. And how this Riemann sum is coming? So we want to solve a problem to finding area under the curve. So we are decomposing that area into several rectangular strips. So the height of rectangle is given by the functional value f of xi, and the breadth of rectangle is given by delta of xi. And now the question is, how can we introduce more and more rectangles in between that area? So for that, we use the help of partition. So we will define what is a partition of that closed interval AB, and then we introduce a norm of P, which is the norm of a partition. So if we apply norm P going to 0, then using this limit, we can introduce more and more rectangular strips in between the area. Okay, so here the whole limit with the sum is known to be the integration a to b f of x dx. That means this is the definite integral. So definite integral is the limit of Riemann sum, where this is our Riemann sum. Okay, so in exam or in mostly in general cases at our level or at this level, maths 1 or maths 2, you don't have to compute the integral using this particular method. So that means you don't need to go to Riemann sum, find the limit and those things. It will be a little tough, but yeah, you don't have to do this. We have other methods to find out the integration, and that is known to be fundamental theorem of calculus, which makes our life very easy. Okay, so just understand what is the integration means. So this is the starting of integration theory of integration, and it goes way beyond now. So that means here we are just living in real to real, but there are several cases. But main thing is, this is the starting point of integration. The problem is finding the area under the curve. The solution is introduce so many rectangles in between the area, and we can get our solution. Okay, I hope that is clear. Any doubt so far?
No, ma'am.
Ma'am, this P is P. These two lines with P. What is that actually defines? That's a partition between 0 and
Norm.
1, right?
Yeah. P is
That's
the
a.
partition, and
Uh,
this whole thing is norm of P.
okay. So what is can you repeat, ma'am? What is the norm of P? Is highest width.
Yeah, highest length of between any 2 points. So, for example, if I take 0, 1, 2, and 4, and then I'll take 10. Okay, so suppose this is your P, a partition P of close interval 0, comma 10. Okay, so now here what will be norm? So the distance between these 2 points is 1, distance
Hmm.
between these 2 points is 1,
Okay.
distance between these 2 points is 2, and here distance is 6. So 6
Okay.
will be your norm of P.
But why in this case? So what we are saying is it is not the n. Each is not equally partitioned,
Mm.
but there's a varied width of the rectangles.
Yeah.
So in that case, why we are choosing only the highest one to be tending to 0? Why not the lowest? I mean,
See,
why can't?
if highest tend to 0, then lowest automatically tend to 0, right?
Oh, okay, okay, okay,
Yeah.
okay,
But the
okay. Understood.
other way around, we cannot say.
Yeah, yeah. If it's lowest, then highest will never be 0. Okay,
Yeah.
understood. Thank
Okay. Fine. So that's how we define integration, definite integration from closed interval a comma a to b. Okay, but we never uses this Riemann sum method to find out the integration of complex functions. Complex function means if you have equation of line suppose 3x plus 2, then yes, you can find out this integration using Riemann sum. But that's also will take 20 to 15 minutes to use Riemann sum to introduce partition and all those things. So it's a very difficult approach to find out the integration. So for that, what we have done, we have introduced the concept of antiderivative. Okay, so what is an antiderivative means? Antiderivative. So as the name suggests, antiderivative is the reverse process of differentiation. So we say a capital F function is an antiderivative of a small f function if you compute the derivative of capital F, it will become small f. Okay, for example, if you have a function small f of x to be equal to 3x square. Okay, so suppose small f of x is equals to 3x square. Then you can observe that if you consider capital F1 of x to be equal to x cube plus 1, then here obviously capital F1 dash of x is 3x square. Right? So we can say that this capital F1 of x, which is x cube plus 1, is an antiderivative.
But it need not be 3x cube plus 1, ma'am. It can be
Yeah,
3x cube also, no?
yeah. So
X
that's
cube
why,
also will lead to 3x square.
yeah. So x cube plus 1, x cube plus 2,
Yeah,
or
whatever.
any,
Okay,
whatever
right.
constant we have.
Okay.
Yeah. So that's why I'm saying an antiderivative. So antiderivative of any function need not to be unique. The reason is simple because we can add a constant, and because the derivative of a constant will become 0. So if we
Okay, okay,
differentiate it,
okay.
it will just vanish.
So x
So
x cube plus 1 or x cube plus 2 will result into x3 x square.
yeah, correct. So f2 of
That's what
x,
you.
if you compute simply, if you take x cube, then this is also an antiderivative. This is also antiderivative of same function f of x is equals to 3x square. So antiderivative is not unique.
But for simple functions like x cube, it's very easy to find antiderivative. I don't know about it will be more difficult to find for a
This is known
complex
to be the
function.
integration. See, that's why we have formulas that integration
Yeah,
of
yeah.
x to the power n dx is
Okay, okay, okay.
x to the power n plus 1 upon n plus 1 plus c. So
So to
this
find a
here,
antiderivative, you have to use the integration formula.
yeah, so this is known to be antiderivative. This is
Okay.
the antiderivative. And this is the notation for antiderivative. So we use integration sign to denote antiderivative. And this antiderivative is also known to be indefinite integration. Okay. So that means there are two types of integrations. So one is the Riemann integration, integration a to b f of x dx. And another one is the antiderivative integration, which is simply f of x dx. Okay, and we can relate these to integration using fundamental theorem of calculus.
So on
Fundamental
the
theorem.
so on the left side you have limits a to b. Here in the right side formula there is no limit.
Yeah, there is no limit because this is
Okay.
defined like we have to find a function whose derivative will become this function.
Okay.
But here we have to do all this limiting business and all partition,
Yeah.
introducing a partition and all this.
Mm.
So what does fundamental theorem calculus did? So it says that the value of integration a to b f of x dx is actually the value of f of x dx computed over two limits a comma b. Right? So this also written as so suppose if you say that capital F of x is integration f of x dx, then integration a to b small f of x dx is actually equal to capital F of b minus capital F of a. Right? Where this capital F is antiderivative of small f.
Ma'am, it's a little bit fast, ma'am. Can
Yeah.
you repeat once again? I couldn't follow this. This
Yes.
up to the this integration of two types is clear. I think
Mhm.
after that it become.
Yeah. So the fundamental theorem of calculus says that if you want to find out the definite integration, then you don't need to go back to the limits and all those things. What you can do, you can just simply find out the antiderivative of small f. That means you will find out that function whose derivative will become small f. And then the value of this definite integration will become the f of b minus f of a. So that means the value of that function at point b minus the value of that function at point A. So let me take one example. So I'll take very simple example. So suppose what is the value of integration 0 to 1 x cube plus 3 dx. Okay. So what is this value? So if you want to compute it by the Riemann sum and all those things, you have to do a lot of work. Okay. But what you can do, so let me take one antiderivative of this function. So here small f of x is x cube plus 3, right? So if you consider capital F of x to be, what do we need? We need a derivative. So if you consider x to the power 4 by 4 plus 3x. Okay. So if you take this function to be capital F of x, what we observe here is capital F dash of x is nothing but 4x cube by 4 plus 3, which is nothing but x cube plus 3, which is our small f of x. So what we have done, we have find an antiderivative of small f. Then fundamental theorem of calculus says that the value of this integration 0 to 1 x cube plus 3 dx is actually nothing but capital F of B minus capital F of A, right? So you can find out f of 1 and f of 0. So f of 1 is nothing but what function we have, x to the power 4 by 4. So this is 1 by 4 plus 3 minus 0 minus 0. So the answer will be 13 by 4. Okay. So
So
that
this,
means
ma'am, this integral of 0 to 1 x cube, that in that equation, what is this f, capital F of, what is that, ma'am? 1.
capital F of 1.
1.
This
Oh,
one.
that's a limit. You are taking limit.
Limit.
Okay.
Yeah.
Limit minus f0. Here
And this
f1,
is, yeah, F1 you can find out from here,
yeah.
right?
But we are
And
not
this,
using differential, no, ma'am.
yeah, we are using
Oh,
f
okay.
dash.
This x, okay, understood. X 4 by 4 plus 3x. Okay.
Yeah. So whatever
Understood.
you have learned the integration in your 12th standard,
Mm-hmm.
this the theory behind that is the fundamental theorem of calculus, that it will relate these limiting
Okay.
integral with our old antiderivative.
Okay. So here, when you are subtracting, always you should take the upper limit first and the lower limit subsequently.
Yeah.
If you take the other way, then you will get a negative value, I
Yeah,
guess,
you will get a negative values.
which is invalid. Okay.
Uh-huh.
Okay.
So that's why we have a formulas, right? So we have
Yeah.
integration formulas. So these
So to
integration formulas are the antiderivatives only.
okay. So to find the to
Capital
find
F.
capital F, we have to
uh,
use the derivative of the given f of x function.
Right. And for finding this capital F, you have to learn integrals formulas.
Yeah.
And then just substitute the limit, whatever we have learned in our 12th
Okay.
standard, that
So
will.
once you find the capital F, you don't have to do F dash because it's only cross checking.
Yeah,
If
it's
you
just only cross checking.
yeah, so if you're able to find capital F, then you straight away substitute the limits, upper limit and lower limit into that F capital F, and then you will get the final value.
Right.
Okay, man. Thank you.
So this is fundamental theorem of calculus. Okay, so I have given you the PDF. In that PDF, you have derivative as well as integration formulas. So that much, this much formulas are more than enough. So there are 22 and 20 formulas, I guess. All basic formulas. So this much formula for our course is actually more than enough. Is that clear? Any doubt? Okay.
This formula sheet is one-to-one matching. Man. Each time that left-hand side derivative will be the antiderivative on the right side. In the formula sheet, there
Yeah,
are
yeah.
two columns.
Yeah. So they have matching. So
They are
here
matching.
the
Okay.
constant is becoming 0. So here the constant is becoming x plus c.
Okay.
So
But
something similar.
but they are not one-to-one, ma'am. Actually, if you see one column has 22 list, another is 19.
Yeah, because they have introduced some rules of differentiation. The product rule, quotient rule, chain rule
Okay.
also.
Okay. Okay.
That's why. Okay. Now,
Ma'am, I
yeah.
have a
So
question.
yes, sir.
So, this Riemann sum, I hope we
Hmm.
won't be questions to be solved by Riemann sum, right?
Yeah. So, but in your activity, I think there are 2 to 3 questions based on Riemann sum. So finding out. So have you guys know the left Riemann sum, right Riemann sum, something like this?
No.
In our lecture, I don't think sir have introduced left Riemann sum, right Riemann sum.
Yes.
So if there are any questions based on left Riemann sum, right Riemann sum, or all the questions based on left Riemann sum, right Riemann sum, I'll try to cover them in lectures only. There is one question I remember which is based on Riemann sum, but other ones I don't.
Okay.
Yeah, but in exam you won't get any question from find the integral using Riemann sum
Okay.
because that will take at least half an hour.
Yeah,
So
yeah.
that's
Okay. Yep. Thank you.
okay. Uh, so now, yes. So as we have several rules in differentiation, product rule, quotient rule, and those things, some similar type of properties also we have here. So the integration of two functions f of x plus g of x. You can distribute integration over addition. That means integration of f of x dx plus integration of g of x dx. Same thing you can do with minus also. Right? So this much you guys know. And also you can pull a constant out from integration. So that means c of f of x dx. This is same as c into integration f of x dx. This is another rule. Another rule is as in the differentiation we have a product rule. Similarly, here we have a quotient rule. Similarly here we have a integration by parts. Okay. So integration by parts means integration by parts. If you have a two function and you want to find out integration of f of x dx, then what you will do, you will take first function, integrate the second one, gx dx, and then you will take minus of integration into differentiation of first function, and then again integration of second function, and then the whole integration. I hope this rule is familiar from your high school. So this is known to be integration by parts. So if you want to integrate the product of two functions, this is equal to the first function into integration of second function dx, and then minus of integration of this whole factor. This factor is containing the f dash of x into integration of gx dx and then into of dx. Okay, so this is the integration by parts. But what happens if you want to find out a to b? So that means if the limits are there, then what else you have to do? You have to apply the limits after computing the integral. So that means you will apply the limit over the whole factor. First you will find f of x integration gx dx and minus of integration of f dash of x integration of gx dx and then whole integration, and then you will apply the limit a to b. Okay. So I'll take one example here. So suppose if you want to find out what is the integration of log x. dx. Okay, so or else I'll ask this you guys. So let's take another example. Suppose x e to the power x dx I want to find out from limit 0 to 1. Okay, so so what will be our approach is to take one function as your f of x, another one as your g of x, right? And for finding f of x, if you guys know, we have used some formula known to be some islet or something, right? So that means first thing, so for f of x, so your first preference will be polynomials. Your second preference will be, I guess, rational functions or something will be there. Your third preference will be logarithmic function, and the last preference will be exponential. Some rule is there, known to be islet or something, if anyone knows. But ultimately, you have to consider polynomial first. Okay. So here, what is our polynomial? Polynomial is x here. So you can take this as our f of x and e to the power x as g of x. Then by formula, we have to take f of x, which is x, integration of e to the power x dx minus integration of derivative of x, which is 1, into integration of e to the power x dx. Limit is from 0 to 1. So here integration of e to the power x is only e to the power x. So x e to the power x minus integration of 1 and then integration e to the power x dx 0 to 1. Again, this will become x e to the power x minus e to the power x 0 to 1. So this will become e minus e and minus 0 minus minus plus 1. Right? Because if you substitute 1 into e to the power 1 will be 1, will be e, minus e to the power 1, and then minus of 0 multiple of e to the power 1, and then plus 1. So the answer will become 1. Okay, so that's how we can apply integration by parts. Any doubt in integration by parts? See, choosing f of x and g of x need a little bit of practice. So as you do much more questions, you will get an idea which function you need to choose as f or which function you need to choose as g. Is that okay?
Ma'am, this second term in your example, integration of f of x, right? So you're taken x into sorry x into integral of ex dx. This part is clear. Minus
Okay.
integral of 1.
Hmm.
F, so you have to say
So
take integral of f of x. F of x is x. So x is
f dash
constant
of
is
x.
f dash of x. Okay. F dash of
Hmm.
x. Okay.
Now it will
Yeah,
become.
it's differential. Okay.
Hmm. Okay, so I'll give you one question to you guys. So try to figure it out. So find out the integration of log x dx, the general integration form. Okay. So here you have to use the trick that you have to consider this as 1 into log x. Now it will be easy. So don't assume it only log x function. Assume it as 1 into log x function or log x into 1, whatever way you want to think.
So because you don't have a direct log integral
Hmm.
formula, is that right? Is that the reason?
Yeah, we don't
Log
have
x
a.
formula is not there, so you are trying to differentiate. Instead of integrating, this log
Yeah,
x will
you
come
have
in
to
the
use
differential term.
integration by parts.
Okay.
So for integration by parts, choose wisely which function you can take as f of x. You know the derivative of log x, right? Log x derivative is 1 by x.
Ma'am, can you slightly scroll up to see the formula of the
Yeah.
by parts? Yeah, just
It will be x log x minus x, I think, plus c, some constant.
Yeah. You have to add plus c. Okay, so here what we have to do, we will consider 1 as our g of x and we will consider log x as our f of x. The reason is we know the differentiation of log x. So differentiation of log x is 1 by x. That's why we are treating that log x as our f of x, right? So by the formula, it is nothing but f of x into integration of g of x dx minus integration of f of x, then again integration of g of x dx, and then whole integration dx. Okay, so if we substitute here, it will become f of x, which is our log x, into integration of dx, which is integration of 1 dx, minus integration of f dash of x, sorry, f dash of x means 1 by x. Now integration of 1 dx and then whole dx. So now it will become integration of 1 dx will become x dx. So that is x log x minus integration of, here we have 1 by x into integration of 1 dx will become x, right? Dx. So this x and x will get cancelled out. So here we get x log x minus with integration of 1 dx, so which is nothing but x log x minus with x dx, and you can add a constant.
Why is that constant, ma'am? Extra constant?
Yeah, see, we are taking antiderivative, right?
Okay.
That's why. So whenever you use integration without limits, you always add a constant, because it says that this integration without limit is an antiderivative, and an antiderivative differ by a constant. So here the value of c depend on situation to situation. So you will know the importance of c when you go in some differential equation type of thing. But you should remember, whenever you treat an integral without limits, you will add a constant.
Hmm.
Okay.
Why is there x dx?
Sorry. Yeah. Fine. Okay. So this is known to be integration by parts. Now there is one more method known to be integration by substitution. Okay. So these are just methods for finding integrals. So finding integration can be too complex. If you know some integrations which are very tough to calculate. So in your high school also there are some integrations which are tough to calculate, but we have some general method which is substitution. Okay. So as the name suggests, we have to substitute something to simplify our integral. Okay. So suppose you have an integration of this type, that integration from some a to b, f of g of x. So here I have composition of two functions into g dash of x dx. Okay. So here you have to judge which function is your f function, which function is your g function. Okay, and all those things. So suppose you have such type of integration, then what we can do? We can use some type of substitutions to simplify these integrals. So what are the things we can substitute? So I can say that, okay, let's take g of x to be equal to t. Okay, then what I can say that, okay, since g of x is equals to t, g dash of x dx is nothing but dt. So that means this whole term can be replaced by dt, right? So again, the second thing is this term. So this f of g of x can be replaced by f of t. Now we just left with the limits. So the limit says if the value of x is a, then we can say that, okay, the value of t is g of a. So I can also replace limit as g of a. And if the value of x is equals to b, then the value of t is equals to g of t. So it's from g of a to g of t. So we have somewhat this changed this complex looking integral into some simpler looking integral just by doing some type of substitution. So this method is known to be integration by substitution. So let's do a couple of examples over here. So suppose we want to calculate integration of suppose x e to the power x squared dx. Okay. So then what will be your suggestion? Which thing we need to use as a substitution?
X square can be
Right.
taken
So we
as a
can take
term,
t as x square.
x square.
So
So it will
then,
become x into e to the power of t.
correct. So that is 1 by 2 dt is equals to x dx. Now we will also, if we have limit, then okay. If we don't have limit, then also okay. So x dx can be replaced by dt by 2 and just e to the power t. The answer is 1 by 2 t. Okay. So now suppose we have example like integration of px. Suppose I have some x cube plus 2x plus 1. Here I have 3x squared plus 2x. Now here what will be your substitution? What should I take as our t?
X square plus 2. No? No.
Is that will work? X squared plus 2. So then dt will become 2x dx. It won't work.
Yeah, it will not work.
This is extrema.
Ma'am, your audio is breaking, ma'am.
Hello, am I audible?
No, it's breaking. We are able to hear you, but the voice is not clear.
Maybe it's the network issue. Okay, I'll try to use earphones. Hello, am I audible now?
No, it still is breaking, ma'am. I don't know others are able to hear or not. I'm not sure.
What about others? Are you guys able to listen?
I can hear clearly.
Okay, maybe
Okay.
it's on my side. My side, possible.
Yeah, maybe. So, yeah, let's get back here. So, what we can do, this substitution actually won't work. So, here you can observe that if you take this denominator as your t, then the differentiation of this denominator is the numerator. Okay, so if you observe here that if we take the value of t to be equal to simply x cube plus 2x plus 1, then dt will become 3x square plus 2, right? Which is nothing but our numerator. So this is into dx. Okay, so here this substitution will simplify our integration. So that means if you take t is equals to x cube plus 2x plus 1, dt is equals to 3x square plus 2. So this integration will become dt by t, right? And integration of 1 by t is log t actually. So the answer will be log t. So that's how you have to use method of substitution. But again, it will take a little bit of practice to judge which function you have to take for substitution. Okay, is that clear?
Yeah.
Okay. So yes, so these are the things we need to learn in this week. Another topic. Yeah, that's all. So any other topic which you guys think I have left? I think I have covered almost everything. Anything which is not clear? Also, see, in week 9, you have to focus on these 5 topics only. Riemann sum and integral also you can, if you don't want, if you think it's not that much worthy, you can just understand the concept and leave it. But this maximum minima, computing area under the curve, antiderivative, fundamental theorem of calculus, these are important. Fundamental theorem of calculus means finding the value of integration a to b f of x dx using integral formulas. Using formulas and methods, whatever we have discussed so far. Okay, so now there is one thing which we can understand is finding the area under the curve. Okay, so this is area under the curve. So suppose if you have some simple curve, suppose something like this, and if you want to find out the area from x is equals to a to x is equals to b, what you will do, this area a, so area a is nothing but integration a to b f of x dx. Okay, so this is the simpler one. Just compute integration a to b f of x dx, you will get your area. But what happens if we have more than one curve? So if the question arises, find the area with the boundaries as f of x and g of x. So they will give you two functions and say that find the area enclosed by these two boundaries. So suppose and x is equals to a and x is equals to b. So here you have four boundaries: f of x, g of x, x is equals to a, x is equals to b. And assume that figure look like this. Okay, this is your the first one is your f of x, and the below graph is g of x. And here is our boundary x is equals to a, and here is our another boundary x is equals to a. Okay, so in this case, what we need to do, we will first break down this particular interval into two parts. So we will say that since this is an intersection point, I'll take this as x is equals to c. First, I will find out this shaded region area, and then I will find out this shaded region area. Okay, because what is the difference between these two areas is, here the lower boundary is g of x, and here the lower boundary is f of x dx. Okay, so if you assume that a1 is this particular region's area and a2 is this particular region's area, then by integration we know that a1 is integration a to c. First we will do f of x minus g of x dx, right? And the area a2 is our integration c to b. And here, since the upper boundary is g of x, we will do g of x minus f of x dx. Okay, and then we can just compute a1 plus a2. That will be our total area. Okay, the reason we are switching the function is because of the upper boundary and lower boundary, right? Here, so for finding a1, what we have done, so here observe, if you want to find out the region a1, right? This is our a1. Here this is f of x, here this is g of x. So what we are doing, we are just finding this whole area, and from this whole area we are subtracting the area enclosed by the curve g of x. Okay, so we'll get our required area. That's why we are doing f of x minus g of x. Okay, and here we are doing g of x minus f of x. Is that clear?
Yes, ma'am.
Okay, so yes, that's all now.
So more number of breaks are there, you can do that same, that many number of terms will come. For example, instead of x of c, if I want to have two such variations are there, it will become c1, c2.
Yeah, correct. For example, if you want to find out the area of modulus of something, right? So obvious, their general type of question is, I forgot now. Suppose -1 to 1 modulus of x dx. Okay, if you want to find out this area, what you will do? Break this area into 0. So -1 to 0. So in this interval, because we know modulus of x is x when x is greater than or equal to 0, and minus x when x is less than 0. So in this part, -1 to 0, we have to take minus x dx, and then plus 0 to 1 x dx. Okay, so this will give us the integration from -1 to 1 modulus of x dx. So this will become minus of integration -1 to 0 x dx plus integration 0 to 1 x dx. So this will become minus of x square by 2 and plus of x square by 2. Here the limit is -1 to 0. Here the limit is 0 to 1. So this is minus of it, take 0 and then -1 by 2 and then plus 1 by 2 plus 0. I'm just doing the computation. Okay, 1 by 2 plus 1 by 2, 1. So that's how we can find out the integration of piecewise function too. Decompose the limit according to your expression. Okay, if x is there, then use x from the required from the given limit. Use minus x from -1 to 0. Okay.
Ma'am, this when you in this equation you got one, right? At the end of the calculation you got one. That is the area under the curve x mod. Is that what you
Yeah,
see?
right. Because see, this is the modulus function.
Right.
So this area, this is -1 plus with this area. So you can
Okay.
also compute by area of triangle too.
Yeah, yeah. It's not intuitively it is not obvious, but I think once you draw the graph, okay.
Yeah, now it is okay. Okay. Yeah, so that's all. So let's quickly recall whatever we have done. So we have learned what is the maximum minimum value of function, how to find them using the second derivative test. Here we also learn about turning point and critical points. And there is a difference between them, that every turning point is a critical point, but the converse is not true. So this is a one portion. Then we introduce this Riemann sum. What is a Riemann sum is, and how this Riemann sum changes into definite integration. That is integration a to b f of x dx. Okay. So after that we have a fundamental theorem of calculus which relates this integration a to b f of x dx as capital F of b minus capital F of a, where what is this capital F function? It's the antiderivative. That means the derivative of capital F of x is small f of x. And then we have some methods to find the integrations. That is integration by parts, integrations by substitutions. Okay. So these are the only topics we have covered in today's lecture. Anything which is left or anything in any topic you guys have any doubts? So have you guys watched the lectures yet? Because yesterday was the quiz. So how's your quiz?
This was okay, ma'am. Probably I didn't have sufficient time to finish the paper. That's so. But whatever I was able to complete, I think today evening there was an answer sheet was released. So I checked the answers. Seems to be okay, but naturally that speed is not sufficient.
Okay. So is the question paper was a little lengthy?
I don't know. Maybe others may be able to do it. I may not be able to do it. So it's very subjective nature.
Okay.
I cannot say.
What about others? What you guys think about quiz 2? They don't think anything.
In one or two cases, I know I made some silly mistakes, and then at the end, I figured out the answer was not possibly correct, and then I went back and I figured out the error where, and I corrected. So thereby, I lost some time. But invariably, whatever questions I could answer in that list, all came through well. But some
Okay.
I couldn't answer because one is lack of time, the other one is. Uh, Possibly more on the limit side. Still I need to practice the limit questions. I could basically carefully avoided, not not because I didn't understand the concept, but I think needs more practice.
Yeah.
Mostly the questions which I attended and I got through very easily was the distance using. There was one question using log, but distance between A B C. So they asked us to find out the x value when the distance between A to B is same as B to C. But the coordinates what they gave is log comma 0, log comma 0, and log comma 0. So basically, when you do that, distance formula with the root cancel out, and then I need to do some calculation, but invariably it went well.
Okay.
So I could choose such questions where the combination of week 1 to 4 with week 5 to 8, I could choose such combinations, and I could do, and few other combinations I selected was mostly lap the derivative L'Hopital rule. Derivative rule. So there was one or two questions around that. So those things I could do. A limit one was slightly, I tried to dodge or avoid not answering. I know I couldn't get. And by the time I finish these things, the time is over. So I just left it there.
Yeah, it's okay.
I don't know about others experience. So that's the reason I couldn't say whether the paper was lengthy or not, because I had my own set of troubles in the answering some questions.
Right. I just complete this calculus part. So that means before week 9 part, you should complete before the release of week 10. Okay, that is my advice, because week 10 and 11 will require more time. So obviously 2 weeks should be fully dedicated to graph theory only. Then only you will be able to understand.
Okay.
So it's better if you guys completed all calculus part up to week 9.
Okay. And week 12 will be The next exam, the final exam is on 13th, right, ma'am?
Yeah.
So you will not get any prep time, I think, because week 12 will go up to
No,
possibly
there is no week 12 in our course actually.
Okay, only up to week
Only,
11.
yeah, only up to week 11. But this week 10 and week 11 is actually very big. So these will contain 10 lectures. This is also contain 10
Okay,
lecture, and there are
okay,
so many topics.
okay, understood.
Yeah. But it's okay. So we'll take some sessions.
Sure.
So you have English lectures, you also have Hindi lectures, you also have revision sessions. We can cover it. But the
Okay.
thing is, you should cover, I mean, just revise everything and uh, particularly sit for graph theory. Because
Sure.
in the question paper also, there will be, uh, I'll say 40 to 45% will be from graph theory, surely.
Graph. Okay. That is between 11 and 12. Sorry, 10 and
Yeah,
11.
10 and
10,
11.
10 and 11. And naturally, 10 and 11 cannot be covered until you are clear with week 9 and earlier part, week like limits and week 9
No.
integration.
It's very independent from calculus part. There is no
Oh,
a single word of a calculus in these 2 weeks.
okay. But
It's very
40%.
independent.
So 40% of the questions can come from week 10 and 11, but which are
Yeah,
independent from week 9 and earlier sessions.
yeah,
So that's a very good input actually. If you can focus very well on 10 and 11, then we can maximize our scoring.
yeah. And the
Hmm.
questions will also not that difficult. They will be on only average, but it's a
Okay.
new topic, so it will take a little time.
Sure, ma'am. Sure.
But it's logical. It's not about it's not like calculus that something is happening and we don't know how it is going
Uh,
to. Uh-huh.
substitution. We have to find out do some
Mhm.
magic to find out what should be substitute.
Yeah, it's not like that. It's just logical. So we have some steps. If you carefully do those steps,
Yeah,
we
yeah.
can get our result.
Sure. Okay.
Okay.
Good. That's a good input.
Okay, so we can wrap up our session here. Thank you guys for joining.
Okay, ma'am. Thank you very much. Have a good night.
Good night.
Hello?